This lesson is going to be about significant figures. Please take notes in your journal and be prepared to ask questions in class. There will be a video response form for you to fill out and show me that you watched this video. When we talk about significant figures, I want you to try not to focus in on the word significant as what we normally mean. You normally mean significant. When you say significant, you're thinking important, like important figures. But that's not what it means here. So I need you to be open-minded and be willing to accept a new definition for significant. And figures refer to digits or numbers. Significant figures are all the numbers that we know in a measurement plus one uncertain or estimated digit. All measurements include all the accurately known digits and one uncertain or estimated digit. First, let's talk about the rules for which numbers in a measurement that you're given are significant, and then we'll talk about how to work with those. Sometimes significant figures are called sig figs for short, and sig dig stands for significant digits. First of all, rule number 1, all non-zero digits are significant. So in the number 514, there's 1, 2, 3 digits that are not a zero. So that's 3 sig figs. In the number 2.3, 2 sig figs. Technically, these should have units with them, right? Or they won't be really measurements. Rule number 2, leading zeros are not significant and are only placeholders. Leading zeros mean zeros in the front of a number, whether they're before or behind a decimal. So, for example, 0.0005, the zeros in front don't count, so that's only one sig fig. 0.023, leading zeros never count, so 2 sig figs. 0.14, 2 sig figs. Guess how many in 0.0087? Right, it's also 2, because the leading zeros in front, never count. Rule number 3, captive zeros are significant. We sometimes call this the Oreo cookie rule. What that means is if there are any zeros in between non-zero numbers, which are significant, then the zeros in the middle become significant also. 1002 has 4 significant figures because the 1 and the 2 are not zero, therefore they're significant, and the zeros in the middle are captive, so that makes 4 sig figs. 20.4, 0 in the middle counts because of the Oreo cookie rule, so that's 3 sig figs. How many sig figs here? Did you say 4? That's right. How many sig figs here? That's right, they're 5. Rule number 4, trailing zeros. This means zeros at the end of a number. Whether or not we consider those zeros significant depends on whether or not you can see the decimal or not. In the number 23.0, we can see the decimal, and so this zero is considered significant. So 23.0 has 3 sig figs. In 101.0, the 0 at the end counts because we can see the decimal. So that's 4 sig figs. This 0 counts because it's in between 2 non-zero numbers. 2.000, 4 sig figs. How many in 18.070? There's 5. Now what's the difference between these two? Let's say they're measurements and they should have a unit. This is 200, this is 200. Your calculator doesn't know the difference, but do you? How many sig figs in 200? Can you see the decimal? Neither can I. So these zeros don't count at the end. That means the number 200, the 2 is just the estimated place. Somebody ballpark estimated something at 200, so it has only 1 sig fig. Now 200 with the decimal at the end, because I can see the decimal, it makes this 0 significant. So this one has 3 significant figures, and it means that somebody at least measured 200 to the nearest tens place and estimated that there were no more things, whatever they were counting, beyond that. Rule number 5 will be a little hard for you to pick up from a lesson like this until we start solving some problems. But I'll tell you anyway, and you can just file it away in your brain somewhere for right now. Rule number 5 says counting numbers and defined constants don't count when you're trying to figure out whether to use that number of sig figs in a problem. For example, a counting number, a defined constant, would be like 7 days in a week. Well, there's no uncertainty in that. So the number 7, you could sort of think of it as having an infinite number of significant digits. It doesn't really, but in this problem it would. And we'll work on that some more, so don't worry if you don't get that yet. Rounding off. When you need to do some calculations with measurements, you have to sometimes round off your answer. How do you know when to round? Well, your answer can't be any more precise than your least precise piece of data. And how many sig figs you decide to round off to depends on what kind of calculations you're doing. Let's take an example that we want to round these numbers to 3 significant figures on purpose. Well, what I do is I look at the 5 here. I say I want 3 significant figures, so 26.54 would be 1, 2, 3 digits, and then to the right I have a 4. If it's less than 5, I'm going to just round it off, keep the 5 like it is. But if it's 5 or more, I'm going to take the 5 and round up. If you get into physics or you take some more sophisticated chemistry classes, the rules get a little bit fuzzier and more accurate. But for our purposes, this is going to do fine. Okay, what if we want to round 2.769 to 3 significant digits? Well, I'm going to take the 2.76, keep that, and the 9 tells me that I need to round that 6 up. Why don't you take a minute and try the next 2, and then I'll come back to you. Actually, I'm going to pause here and put more of these problems in the next recording.